Welcome to Stochastic Processes, lesson number 10. We're going to talk about Poisson processes in this lesson. In the previous lesson, we established two things. Continuous time forces exponential holding times because of the memoryless property permits nothing else. And counting processes, which we defined towards the end of the lesson, become tractable when they have independent and stationary increments. The Poisson process is what you get when you put those ideas together and add a rate. That's the lambda we talked about. It is defined by four short axioms, which we'll see on the next slide. And almost everything else follows by a proof, and we'll see a couple of proofs in this lesson. So that's what makes this elegant. A very small number of assumptions will yield a great deal of structure for the Poisson processes. So we'll state the axioms, prove that the interarrival times are also exponential, arrive at the Poisson distribution, and finish with three variations of the Poisson distribution, merging and splitting, the non-homogeneous case, and the compound process. These are the four axioms or properties that a counting process needs to have in order to be defined as a Poisson process. The n of 0 equals 0, so counting starts from 0. N of t has independent increments. You remember we had those two properties from the last lesson, independent increments and stationary increments. So that's one of the four axioms. One arrival in a short interval has probability lambda h to the first order. This is little o of h is the reference to first order. If you're not familiar with this, I'll explain it on the next slide. And then two or more arrivals are negligible compared with h. So they're just order small o of h. And then you may be asking, well, we had the independent increments. Why didn't we state stationary increments as another axiom? But that follows from these two here, since neither one of these involve time. You notice there's no t in either one of these. So the process is stationary. In fact, if we added t, which we'll do later on slide 10, we'll get what's called a non-homogeneous process. We'll see that later. Axioms 3 and 4 from the last slide use this notation here to read little o of h. A function f is little o of h if it vanishes faster than h itself. Technically, it's this definition here. So we can use an example maybe to make it clearer. So if f of x is x squared, then we plug that in here and we get h squared over h, and that's h, and that equals 0. And if you look at a graph of y equals x and y equals x squared, you can see that x squared cuts underneath of y equals x once you get between 0 and 1. So it does approach 0 much faster. And of course, the same thing would hold for x cubed and x squared, any higher power. Then we have another property that we'll use in some of our proofs that follow. A linear combination, in other words, a constant plus times f of h plus a constant times g of h is again order h. And that's just, you take this here, the linear combination, you can just break it into two pieces. You can factor the a out of the limit, and then you're just going to have this twice. So you get 0 plus 0 equals 0. What if we start observing a Poisson process from a later time? It turns out that doesn't matter. We can show that here. Define the shifted process, n sub s of t, in terms of the initial Poisson process. Then our claim is n sub s of t is a Poisson process with rate lambda. The first axiom holds, axiom 1. we have, if you take n sub s sub 0, and using this definition here, you have n of s minus n of s, and that equals 0. Independence over disjoint intervals is unaffected by starting later. That's the axiom II, second axiom. And then the third and fourth axioms carry over directly, shifted by s. So why does this matter? A Poisson process looks the same whenever you start watching it. That is what makes the interarrival argument in theorem 31, which follows, work out. We want to find the distribution for the first interarrival time. So we have a theorem to that effect. The random variable t sub 1 is exponentially distributed. This is what we want to prove. In terms of notation, t sub n is defined to be the interarrival time between event n minus 1 and n. So when we have t sub 1, it's between 0 and 1. T sub 1 is greater than t means no arrival has occurred by time t. So the two events are the same thing. T sub 1 greater than t is the same event as no arrivals occurred by time t, which is this here. Therefore, we need to find a distribution for this. Right, we're going to use this instead of this since they're equivalent. The strategy is to build a relationship between the probability of no arrivals in time t plus h and the probability of no arrivals by time t. So in other words, the difference here is in time is h. We let h go to 0 and then solve the resulting differential equation. On this slide and the next, I derived the differential equation that I just mentioned. I copied axioms 3 and 4 here on the upper right because we'll refer to them, and I made them green just so it didn't confuse with the rest of the discussion here. So what we want to compute is the probability of no intervals by time t plus h, and we can break that into no intervals by time t and no intervals between time t and t plus h. By axiom 2, those intervals are independent, so the probabilities multiply. So we're looking for the probability of no arrivals by time t plus h, that's this here, and we can just break it into no intervals up to time t, which is this, and then no arrivals between time t and t plus h. And the way we get that is the probability of one or more arrivals between t and t plus h. And then we subtract that from 1, and that gives the probability of 0 arrivals between t and t plus h. That's what this is. Then we need to use these two to get this probability inside here, because we want this probability greater than or equal to 1, and this just gives it for 1 and greater than or equal to 2. However, if we take these two together, we add these, then what I mentioned before about if you add functions of order little o of h, any linear combinations is again little order o of h. So this probability, which I've written down here, the probability of one or more in h is just the sum of these two. These two, when you add them together, you get little order h, and then you just get the lambda h. So that's this here, and that's what we plug in for this, which I'm showing here. And we just brought this down, as I mentioned. So then we multiply this through, so you get this quantity times 1, which I've subtracted from the other side, and then this quantity times minus lambda h, and this quantity times little order h, which is again little order h. So we get this here. Then we just in terms of notation, we let f of t equal the probability of no arrivals up to time t. So then we have here f of t plus h. Sorry, I didn't write it all out. We have f of t plus h and minus f of t, and we can divide that by h, and that's basically, if you let h go to 0, that's basically the definition of a derivative. So that's what we do. We let h go to 0, and this is the derivative of f of t. And then on this side here, we've already divided out the h, and this is f of t. And so as you let h go to 0, there's nothing here that involves an h once you've divided h to the other side. And you get minus lambda f of t. And then as you take the limit as h goes to 0, this is just 0. So you get this here. And we can just write that as just dividing the f of t on the other side. And then what we want to do is take the antiderivative of both sides of this. So, and I'll show you that more on the next slide, but I just wanted to emphasize the, just as a reminder, if you have the log of say, g of t, the derivative of that is 1 over g of t times the derivative of g of t. That's from the chain rule. So the antiderivative of this here is basically the log of f of t. So let's move on to that on the next slide. So we took the antiderivative, as I mentioned, this log f of t on the left, and then we had just lambda on the right, but the antiderivative of lambda is minus lambda t plus some constant. But we know that f of 0 equals the probability of n of 0 equaling 0, which that's axiom 1. That's happens with probability 1. So f of 0 is 1. And of course, the e to the 0 is 1. And so you get b equals 1. Okay, so the probability, just plugging things back to where we started, the probability that n of t equals 0 is, making the substitution for b, is e to the minus lambda t. And as we said at the very beginning of all this, that's the same as the probability as the first transition being greater than t. And so we've shown that t sub 1 is exponential with rate lambda. Okay, so what we're going to do next is look at the t sub 2 and t sub 3, and basically the further transition times. Theorem 31, the interarrival times t sub n are independent, exponentially distributed random variables with rate lambda. T sub 1 was settled by theorem 30. Now let's look at t sub 2 and condition on t sub 1 equals s. The interval s to s plus t is independent of what happens in the interval 0 to s. Right, we had the independence of the intervals as one of the axioms. So by axiom 2, the conditioning doesn't matter. So we have the probability that t sub 2 is greater than t, given that t sub 1 equals s, is equal to the probability of n sub s of t equals 0. Remember we defined this earlier in theorem 29 showed it was a Poisson process. So this probability is equal to, is given by e to the minus lambda t. The last step uses theorem 29, which I just mentioned. The shifted process, ns, is itself a Poisson process with rate lambda. That's theorem 29. Since the answer does not depend on s, t sub 2 is independent of t sub 1. So we have exponentially distributed and independent. And then you can do the same reasoning for t sub 3 and t sub 4 and so on. And that proves our theorem here. Okay, so let's continue. A Poisson process is a Markov chain. The state space is the number of arrivals, 0, 1, 2. It only goes up, right? You can only have more arrivals. You can't, at each transition, you can't stay where you're at, and you can't have less. And the probability is 1 in going from I to I plus, state I to I plus 1. Every state has the same exponential holding time with rate lambda. All the randomness lives in the holding times with respect to a Poisson process. Then the probability of having n arrivals in time t is given by this. It's known as the Poisson distribution. You can derive that from the definition of the Poisson process. I'll give you a link to a book that has a derivation of that if you're interested. And then the expected value of this distribution is also equal to the variance of this distribution, and it's lambda times t. In terms of modeling, we could either merge or split a Poisson process if the application requires it. So in merging, let me point to it here on the left, two independent Poisson processes combine into one. We add their rates, and that gives you the rate of the combined process. So I have an example here, business and residential customers at a bank. Maybe you want to combine those together. Type 1 means the arrival came from the counting process or Poisson process n sub 1. And type 2, the arrivals come from a Poisson process n sub 2. Then these are the probabilities of the next arrival. This one on the left is the probability the next arrival is of type 1. And then on the right is the probability that the next arrival is of type 2. Then you can also split the Poisson process. Label each arrival independently. Type 1 was probability p, and type 2 was probability 1 minus p. So of course you would need to estimate those probabilities. Type 1 arrivals form one output stream. Type 2 arrivals form another. And the rates would be p times lambda and 1 minus p times lambda. Both are still Poisson, and lambda here is the rate for the combined process before you split it. We can also have non-homogeneous Poisson processes. I mentioned this earlier in this lesson, but I have a more general form of it in this slide here. So only one axiom changes. We replace the constant rate lambda with an intensity function, lambda of t, that varies over time. This is a better fit for traffic or customer arrivals. So here's the axiom 3 that's modified. In the original form, there's just a lambda here. Now it's lambda of t, so we have a function. The other 3 axioms are unchanged. So independent increments are kept. That's axiom 2. Stationary increments are lost. We now have this function here, lambda of t. Then I'm not going to go through all the computations, but just to give you the result, if we define a mean value function here, m of t, then the distribution for the number of arrivals in time t, by time t, is given by this equation here, or this expression. So it's m of t, this function raised to the n power, e to the minus m of t divided by n factorial. Okay, so that is my quick summary on non-homogeneous Poisson processes. Another extension is compound Poisson processes. As we know, a basic Poisson process allows arrivals one at a time. If we lift that restriction by attaching a random size to each arrival, then we get a compound process. So that's what I have here. X of t is a compound Poisson process. You still measure or model the number of arrivals by n of t, but then each arrival is the number of entities in each arrival is a random variable y sub I. So x of t is the total size of all arrivals. N of t is a basic Poisson process, and the y sub i's are independent, identically distributed, and independent of n of t. Maybe an example will clarify this a little bit. So we can have customers arriving at, say, a bank. That would be a Poisson process, and we would model that by n of t. But then each customer requests a random number of transactions, and that's what we model with this y sub I. So maybe you have a first customer only has one transaction. The next customer is a business customer, and he or she has 10 transactions, and then the next customer has 3. And so it's basically each arrival has associated with it multiple transactions, and that's why you need this type of model here. If y sub I is equal to 1, then we come back to the Poisson process. Then using something called Wald's equation, we can take the expected value of this. It actually comes out fairly directly from Wald's equation. I give you a link here. If you just go to Wikipedia and search under Wald's equation, you'll find it. So the expected value of x of t is lambda t times the expected value of y sub 1. You may wonder why y sub 1. The reason it's that is because these are identically distributed. So I could have put y sub 2 or y sub 3. It doesn't matter. They all have the same expected value. So I just put in y sub 1 here. And then the variance is lambda t times the expected value of y sub 1 squared. And again, same reason for putting y sub 1 here. I could have used any of the y's because they're identically distributed. So this is the last slide in our lesson, number 10. In summary, we had 4 axioms to define a Poisson process. We showed that interarrival times are exponential with rate lambda. We proved that. N of t follows the Poisson distribution. The mean and the variance both equal lambda t. Then I showed some extensions using merge and split. Then lambda can be made time varying. That was the non-homogeneous case. And then we just saw the compound case on the last slide. So coming up in lesson 11, we have birth and death processes, Q's, and what makes them stable. These are particular types of Q's that we'll talk about. And then the Kendall notation for describing a Q. So these are 2 examples of using that notation. So we'll do that in lesson 11. And then there's a lesson 12 that I planned. And then I have later on, after I started doing these lessons, I decided to do a lesson just on problems, and that's lesson 13. So if you like this, please give it a thumbs up and stay tuned for the next few lessons.